All right, so in the first half of these videos, we talked about dipole-dipole interactions and hydrogen bonding. The third major type of intermolecular forces that we're going to discuss are dispersion forces, or sometimes you'll see these called London dispersion forces. So all atoms, molecules, and ions have dispersion forces. But for nonpolar covalent compounds, these are the only intermolecular forces they have. So dispersion forces result from fluctuations in the electron distribution within atoms and molecules. Right, so here we basically have helium atoms, and we've got the electrons whizzing around, the two electrons in helium whizzing around in the electron cloud. At any one instant, as the electrons are flying around, they might both happen to end up on the same side of the molecule. When that happens, within that atom or molecule, there's an uneven distribution of electrons, right? Where temporarily, because the electrons aren't stopping, they're still whizzing around, we have a partial negative side of the atom or molecule and a partial positive side. And so we might call this an instantaneous dipole moment. It only exists for a tiny fraction of time, but it exists as a dipole moment nonetheless for that short fraction of time. So what happens when we get this instantaneous dipole moment is that it can induce a temporary or instantaneous dipole moment in a neighboring atom or molecule. So we get the instantaneous dipole moment in the first atom. The electrons of the second atom see that partial positive charge. They move over because they're attracted to that, and then that can perpetuate to other atoms and molecules. And so we say that the instantaneous dipole moment in the first molecule induces an instantaneous dipole moment in the second atom or molecule, and it causes them to stick together a little bit, right? But as soon as the electrons find themselves on the same side over here, right, we get electron-electron repulsions, which will force them away from each other. And so these are very fleeting, very short-term interactions, but they are attractive interactions nonetheless. Okay, you may have guessed that London dispersion forces, on average, are the weakest intermolecular force. We have these only temporary interactions. That being said, all atoms, molecules, ions, they all have electron clouds. And we can have these sort of instantaneous interactions even if they have some of the stronger intermolecular forces. So all atoms, molecules, ions have dispersion forces. If we have a nonpolar molecules, these are the only intermolecular forces they have. For things that have dipole moments and hydrogen bonding, those tend to often be more important because they're stronger, but the dispersion forces still exist. Now, the term polarizability is related to dispersion forces. Polarizability refers to the ability of an electron cloud to be distorted. And the more polarizable a molecule is, the greater its dispersion forces will be. And so the factors that tend to impact polarizability is atom and molecular size, right? So the larger the electron cloud, the more electrons you have, the easier it is to distort them. And so generally bigger atoms, or when we're talking about molecules, bigger molecules are going to be more polarizable, and they're going to have stronger dispersion forces. It turns out the shape is also very important, and it can impact the strength of the dispersion forces. And so we'll look at that in a little bit more detail on the next slide. So we've got two examples here. I want to know which atom or molecule in each pair would have a higher boiling point. And so in the first one, we have a sample of neon versus a sample of xenon. And so these are both noble gases. Since they're just monatomic, there's no polarity. So the sample of neon or sample of xenon is going to be nonpolar. So all it's going to have are dispersion forces. But if you look at the periodic table, xenon is much bigger than neon, meaning xenon is more polarizable. So it's going to have stronger dispersion forces than neon. And the stronger the intermolecular forces, the harder it is to pull them apart. And so the higher the boiling point will be. So stronger intermolecular forces, in this case dispersion forces, equals higher boiling point. So in this case, a sample of neon and a sample of xenon would both have dispersion forces, but because xenon is bigger, it's more polarizable, it'll have stronger dispersion forces, and therefore the higher boiling point. All right, this next example is going to get to the shape that we talked about before. So in both of these molecules, we have 1, 2, 3, 4, 5, 6, 7 carbon atoms, 1, 2, 3, 4, 5, 6, 7 carbon atoms, and I'm not going to count them, but hopefully you believe me that they have the same number of hydrogen atoms, or you can pause it and count them for yourself. So in terms of the size of the molecules, there's not much difference. They have the same molar mass, same number of electrons. And so in this case, they're also going to only have dispersion forces because we only have carbons and hydrogens. We don't have any polar bonds, so it's impossible to have polar molecules with only carbons and hydrogens. So again, it'll only have dispersion forces. So now it comes down to the shape. And when we think about the shape of this first molecule, right, it's sort of long and skinny. And so if we imagine bringing up another molecule of the same type up next to it, right, there's a lot of surface area where those two molecules are going to interact. Whereas when we have more branching in a more compact molecule like we do in this case, right, if I bring two of those electron clouds, right, we're imagining the electron cloud for the whole molecule is sort of spherical, right, there's much less surface area where the electron clouds are going to interact. And so this is where shape plays a role in dispersion forces. Generally, the longer the molecule chain is, the greater the dispersion forces are going to be, and so the higher boiling point. And so in this case, the first of the carbon and hydrogen compounds will have the higher boiling point. So dispersion forces, dipole-dipole interactions, and hydrogen bonding are probably the main intermolecular forces that we'll use and talk about. But I did want to mention at least a couple of others. And so we're sort of getting ahead of ourselves a little bit, but I think it makes sense to introduce it here, and that is the intermolecular force of ion-dipole interactions. So this is when we have an interaction between something like a sodium ion and then any other polar compound that has a dipole moment, hence the name. It's an interaction of an ion with a dipole. The reason we're getting ahead of ourselves a little bit is because at this point we've largely been talking, with a couple exceptions, about pure substances, where the two molecules interacting are the same molecule. And obviously something can't be an ion and then also just be polar, so this only occurs when we have mixtures that we'll talk about later, but I think it makes sense to introduce this intermolecular force now. So ion dipole, typically when we have mixtures, like if I take sodium chloride, dissolve that in water, the sodium chloride will dissociate, and the sodium ions will interact with the negative oxygen end of the water molecules, and the negative chloride ion will interact with the positive hydrogen ends of the water molecules. In each case, though, these are ion dipole interactions. We also mentioned ionic bonds. And so ionic bonds are kind of weird in terms of intermolecular forces because in ions we don't have molecules, right? We just have the alternating positive and negative ions. But in terms of the properties that bonding forces and intermolecular forces influence in covalent molecules, the ionic bonds sort of influence all of those. And so we can sort of think about ionic bonds as being both intermolecular and intramolecular. If we consider them to be intermolecular forces, they're much stronger than things like even hydrogen bonds or dipole-dipole interactions, and certainly stronger than London dispersion forces. And this can explain why basically all ionic compounds are solids at room temperature, and generally we have to heat them up very high to get them to melt or decompose, and that's because these ionic bonds are basically bonding forces, but they also influence the so-called intermolecular forces, giving them very strong interactions and keeping these ionic compounds as solids unless we get to very high temperatures. Okay, so let's rank the strength of the intermolecular forces and sort of remind us where these all fit in. So the strongest are ionic bonds, because while we can sort of think of them as intermolecular forces, they're also really bonding forces, and so they're much stronger than typical intermolecular forces. The ion dipole would come in next. And we'll really encounter those more when we talk about mixtures coming up in a couple chapters. And then among the what I would consider the traditional intermolecular forces, we have hydrogen bonding, dipole-dipole, and then dispersion or London dispersion forces. Right, we're the strongest, we've listed at the top, and the weakest down at the bottom. All right, I kind of like this flowchart for determining what the strongest intermolecular force in a sample is. Right, so the first thing that we want to do, if we're given a compound, say, what is the strongest intermolecular force that exists in that compound? First question you want to ask is the compound ionic or covalent? If it's ionic, then the quote-unquote intermolecular forces are ionic bonds. If it's covalent, then we have more questions that we need to ask. Is the molecule polar or nonpolar? If it's nonpolar, then the only intermolecular forces it has will be dispersion forces. If it's polar, it certainly at least has dipole-dipole interactions, but if we have a hydrogen directly connected to a nitrogen, an oxygen, or a fluorine, then we can upgrade that dipole-dipole interaction to hydrogen bonding. If we don't have this scenario, the hydrogen has to be directly connected to the nitrogen, the oxygen, or the fluorine. If that's not the case, then the strongest intermolecular force we have is dipole-dipole interactions. And here I'm assuming we're talking about a pure substance, and so that's why the ion dipole doesn't appear in this flowchart. All right, so let's finish off with a couple examples. And so we want to determine what is the strongest or the primary intermolecular force in a sample of each of the following. So I've got two on each slide. So we'll start with barium bromide. All right, so if you want, you can flip back to the flowchart on the previous one. But the first question we're going to ask is the compound ionic or covalent? Barium is a metal, bromine a nonmetal, so we have an ionic compound, so we would say the intermolecular forces are the ionic bonds. All right, now let's consider this CH3COOH. Anytime you see this COOH, this is what we call a carboxylic acid. It's something you'll see a lot if you go on to take organic chemistry. What the Lewis structure of this molecule looks like, I've got this CH3, and then anytime you see this COOH, it's telling us that we have we've got COOH. So we've got a double bond from the carbon to the oxygen, and then that same carbon is also connected to an OH. All right, so we definitely have polar bonds. There's no way this molecule is going to be symmetric. So this molecule is covalent, so I should have started with that. And then it's definitely polar, so it's either dipole-dipole or hydrogen bonding is the strongest intermolecular force. Since I have a hydrogen directly connected to an oxygen, I'm going to have hydrogen bonding in this sample. All right, so now we have ammonia and H2S. So NH3, first question, ionic or covalent? I have two nonmetals, so it's covalent. In the interest of time, I'm just going to quickly draw the Lewis structure. But I think you do need to draw or at least visualize what the Lewis structure is going to look like to answer these questions. And so I have polar bonds. I have 4 electron groups, and so this molecule is going to be trigonal pyramidal. So we've got the lone pair up here breaking up the symmetry. So this molecule is going to be polar. So it's covalent. Then we ask, it's polar. And then we do have a hydrogen directly connected to, in this case, a nitrogen. And so there's going to be hydrogen bonding in a sample of ammonia. All right, H2S. First question, ionic or covalent? Two nonmetals, it is covalent. So then polar or nonpolar, I need to draw the Lewis structure. Again, I'm going to draw the Lewis structure quickly, just in the interest of time. Right, basically it looks like water. So we have polar bonds. It's asymmetrical. It's bent or V-shaped. And so it's covalent. It's polar. We do not have a hydrogen directly connected to a nitrogen, an oxygen, or fluorine, however. Therefore, the strongest intermolecular force will be dipole dipole. All right, last two examples. We have SiH4. It's a metalloid with a nonmetal, but it's going to be covalent. And we could go and look up the electronegativities to see if we have any polar bonds, but in this case, it doesn't matter. Right? This is going to look like methane. It's going to be tetrahedral. I've got no lone pairs. So even if I had polar bonds, it doesn't matter because the molecule is symmetric. And so even if they are polar, they would cancel out. And so this molecule is covalent. It's nonpolar. So the strongest IMF will be dispersion forces. And then our last example, let's look at CH2ClBr. So all nonmetals. So we have covalent. Hydrogen is going to be our central atom. And so this is going to be tetrahedral. And we could mix up and put the chlorines and the bromines wherever we wanted. But however we do it, the molecule has polar bonds. The carbon-bromine bond and the carbon-chlorine bond are polar. They don't have, chlorine and bromine don't have the same electronegativity, so they're not going to cancel each other out. But even if they were both bromines or both chlorines, there's no way we're not going to end up with two more electronegative atoms on one side of the molecule and the two hydrogens on the other. So this molecule does have a dipole moment. The hydrogens are not connected to oxygen, nitrogen, or fluorine. So the strongest intermolecular force in that second molecule is going to be dipole dipole.